Imagine waking up one morning and the world is silent. Not peaceful quiet, dead quiet. No birds singing, no insects buzzing, no distant sounds of animals in the forest. You walk outside and realize that 90% of everything that was alive yesterday is just gone, vanished. Not slowly over decades or centuries, gone in what geologists call an instant, which might mean a few thousand years, maybe a few 100,000. Either way, in the grand timeline of a 4.5 billion-year-old planet, it's a blink, a snap of the fingers, and then almost everything is dead. This isn't science fiction. This has actually happened. Not once, not twice. 5 separate times, Earth has hit the reset button on life itself. 5 times, our planet has transformed from a thriving, bustling biosphere into something that looks more like a graveyard. And here's the part that should keep you up at night. Except, you're probably using this to fall asleep, so maybe it'll give you interesting dreams instead. Scientists believe we might be living through the beginning of the 6th extinction event right now, this moment. While you're listening to this, if you're in Tokyo at 3 a.m. or London at dinner time or somewhere in South America watching the sunset, subscribe and tell me where you are. I read every comment and it's wild to think we're all scattered across this planet that's been through so much. The story of Earth's mass extinctions is the story of apocalypse after apocalypse. Events so catastrophic they make every disaster movie look tame by comparison. We're talking about moments when the rules of survival just stopped working. When being the biggest, strongest, most successful species on the planet meant absolutely nothing. When evolution's greatest success stories were erased like chalk on a blackboard. Take the Permian extinction. About 252 million years ago, geologists call it the Great Dying, and that's not dramatic language, that's just accurate. Roughly 96% of all marine species went extinct, 70% of land vertebrates. Gone. The only mass extinction that came close to ending life on Earth completely. The planet became so hostile that scientists think there were regions where nothing could live at all. Dead zones that stretched for thousands of miles. Or the one everyone knows about. 66 million years ago, when a rock from space 6 miles wide slammed into what's now the Gulf of Mexico and erased the dinosaurs. Animals that had dominated the planet for 165 million years. Just deleted from existence, along with 3/4 of all plant and animal species on Earth. But here's what's really unsettling. Each extinction had a different cause. Some were triggered by volcanic eruptions so massive they make anything in recorded human history look like a candle flame. Others by climate shifts that turn the oceans toxic. One might have been caused by the evolution of plants, if you can believe it. Plants that change the atmosphere so dramatically they accidentally killed off most other life forms. The terrifying lesson is this. There are dozens of ways for Earth to reset itself. Dozens of mechanisms by which the planet can essentially sterilize its own surface and start over. And every single time it happens, the world that emerges afterward is fundamentally different from what came before. After each extinction, it's like Earth spins a roulette wheel to see which survivors get to inherit the wasteland. Small, seemingly insignificant creatures suddenly find themselves with all the evolutionary space they need to become something new. Our own mammal ancestors were tiny, unremarkable things living in the shadow of dinosaurs. Then the asteroid hit, the dinosaurs died, and those scrappy little survivors eventually evolved into everything from mice to elephants to humans. The question that haunts researchers is simple. What could possibly kill 90% or more of all life on Earth? What force is powerful enough to override millions of years of evolutionary adaptation, to make extinct the most successful species across every continent and ocean simultaneously? And the more troubling question, could it happen again? Scientists tracking current extinction rates are seeing something alarming. Species are disappearing faster than at any point in the last 66 million years. not from asteroids or supervolcanoes, but from us, from human activity, climate change, habitat destruction, pollution, overfishing. We might be creating the conditions for Earth's sixth Great Reset, except this time, we're not the survivors hiding in burrows, we're the asteroid. Over the next few hours, we're going to walk through all 5 of Earth's previous extinction events. We'll see what killed the trilobites, what turned the oceans purple and poisonous, what finally ended the age of dinosaurs. We'll watch the planet die and be reborn 5 separate times, and then we'll talk about what's happening right now. Because the evidence suggests that Earth's 6th extinction isn't coming, it's already here. So, get comfortable. Maybe you're in bed in Singapore, or on a night shift in Chicago, or watching dawn break over Sydney. Wherever you are, you're about to take a journey through 4.5 billion years of Earth's deadliest secrets. Let's start at the beginning, or rather, at the first ending. Before we dive into Earth's 5 great dyings, we need to understand what we're actually talking about. What qualifies as a mass extinction? What separates a normal bad century from an actual planetary catastrophe? The answer is both simple and terrifying. A mass extinction is when at least 75% of all species on Earth disappear in what geologists call a geologically short time. Now, geologically short doesn't mean quick by human standards. We're not talking about a weekend. These events typically unfold over thousands to millions of years. But in the context of Earth's 4.5 billion year history, that's basically a snap of the fingers. It's the difference between dying of old age over decades and getting hit by a truck. The outcome is the same, but the timeline is radically compressed. Here's what makes this number so staggering. 3/4 of all species, not individual animals, not populations, entire species gone. Every single member, every genetic lineage, every evolutionary experiment that species represented, eliminated from existence. When we say 75% of species went extinct, we're talking about millions of years of evolution being erased in what amounts to a geological instant. But how do we even know this happened? How do scientists look back hundreds of millions of years and count dead species with any confidence? The answer lies in rocks, and the story they tell is written in the language of absence. Paleontologists study the fossil record, the preserved remains of ancient life trapped in sedimentary layers. These layers build up slowly over millions of years, like pages in a book. Each layer represents a specific time period, and the fossils in that layer show us what was alive then. When you study these layers systematically, you start to notice patterns. In most layers, species diversity remains relatively stable. You see the same groups of organisms appearing consistently, maybe evolving slowly, new species emerging while others fade away. This is normal. This is what scientists call background extinction, the steady tick of evolutionary turnover that happens all the time. Background extinction is evolution's baseline. Species appear, they exist for a few million years on average, then they go extinct, replaced by descendant species or competitors. It's not dramatic, it's not catastrophic, it's just the way life works. Think of it like people dying of natural causes in a city. Every day some people die. Every day new people are born. The population stays relatively stable. That's background extinction. But then, in certain layers, something different appears. You're moving up through the rock, following the timeline forward, and suddenly the diversity collapses. Entire groups of organisms that were abundant in the layer below are just gone from the layer above. Not rare, not declining, completely absent. It's like flipping through a photo album of your family and suddenly finding pages where 3/4 of the people have been cut out of every picture. Someone was there, and then they weren't. These transition layers are called extinction boundaries, and they're some of the most studied and debated features in geology. Scientists can date them using radioactive isotopes in the rocks. They can analyze the chemical composition of the layers to understand what the environment was like. They can track which species disappeared and which survived. And when you do this work carefully, you start to see that Earth's history isn't a smooth story of gradual change. It's punctuated by sudden catastrophes that reset everything. The difference between background extinction and mass extinction is like the difference between normal weather and a Category 5 hurricane. During background extinction, maybe one species out of every million goes extinct each year. It's barely noticeable against the constant emergence of new species. But during a mass extinction, that rate increases by orders of magnitude. Hundreds or thousands of species vanishing every year. Entire ecosystems collapsing within millennia. Evolution's normal rules suspended as survival becomes random and death becomes universal. And here's what really keeps geologists up at night. Mass extinctions don't just kill indiscriminately. They fundamentally restructure which types of organisms can succeed on Earth. Before a mass extinction, certain groups dominate. They're perfectly adapted to the world as it exists. They've spent millions of years evolving to fit their niches. Then the extinction hits. The world changes, and suddenly all those perfect adaptations become liabilities. The survivors aren't necessarily the strongest or the smartest. They're the lucky ones who happen to have traits that worked in the new reality. After each mass extinction, Earth essentially reboots. The survivors spread out into the empty ecosystems, evolving rapidly to fill the vacant niches. New dominant groups emerge that never could have competed with the old guard. Evolution gets a fresh start, exploring possibilities that would have been impossible before the reset. This is why mass extinctions matter. They're not just death events. They're creation events. They're the reason mammals inherited the Earth from dinosaurs. They're the reason dinosaurs inherited it from the mammal-like reptiles before them. They're the moments when evolution's direction changes completely. Throughout Earth's long history, life has faced 5 catastrophes severe enough to earn the title mass extinction. Paleontologists call them the Big Five. 5 moments when the planet came closer to being sterilized than at any other time in the past 500 million years. Each one was caused by different mechanisms. Each one killed in different ways. Each one reset Earth's biological clock and sent evolution spinning off in new directions. Before we continue, I'd love to know where you're experiencing this story. Drop a comment and let me know where you're watching from and what time it is for you right now. Are you falling asleep in New York? Waking up in Tokyo? Having a quiet afternoon in London? It's fascinating to think about all of us scattered across the planet, connected by curiosity about Earth's deep history. Now, these Big Five extinctions follow a pattern. Each one cleared away the dominant life forms of its era. Each one opened up ecological space for new groups to emerge and flourish. Each one demonstrated that no matter how successful, how well adapted, how numerous a group of organisms becomes, they can still be destroyed when Earth systems destabilize. And each one teaches us something crucial about how planetary catastrophes unfold and what it takes to survive them. The first great dying happened so long ago that the world would have been unrecognizable to modern eyes. The second occurred when life was still mostly confined to the oceans, experimenting with the strange new frontier of dry land. The third was the closest life has ever come to total annihilation, an event so catastrophic it makes the others look mild by comparison. The fourth set the stage for the age of dinosaurs, and the fifth, the most famous, ended that age with apocalyptic finality. But here's what makes the story urgent. We're living through what many scientists are calling the sixth extinction. Right now, in our lifetimes, species are disappearing at rates that rival the Big Five. The difference is this one isn't being caused by asteroids or volcanic eruptions or natural climate swings. It's being caused by us. And unlike the victims of previous extinctions, we can see it coming. We can understand what's happening. We can study the past to predict the future. That future is what this story is really about. Because if Earth's history teaches us anything, it's that mass extinctions don't just kill. They transform. They create new worlds from the ruins of old ones. And understanding how that transformation happens, why some lineages survive while others perish, what kind of planet emerges after the catastrophe ends, that knowledge might be the most important thing humanity ever learns. So let's go back to a world so ancient that even the rocks have mostly been destroyed by time. Back to the first moment when Earth looked at the life it had created and decided to start over. Back to 445 million years ago, when something went catastrophically wrong and the first great dying began. Let's go back, way back, 445 million years ago. So far back that the world would be literally unrecognizable to you. Picture this. You're standing on the shore of an ancient continent, but shore is the wrong word because there's nothing alive here. No grass beneath your feet, no trees providing shade, no insects buzzing around, no birds overhead. The land is completely, utterly dead. Just rock, sand, and silence. The only sounds are wind and the crash of waves against barren stone. But turn around, look at the ocean. Because that's where everything is happening. This sea's absolutely teeming with life. Not the life you know, not whales and sharks and coral reefs as we understand them today, but something alien. Something that would look like science fiction if you could see it. The dominant creatures are trilobites. Imagine something like a horseshoe crab, but there are thousands of species, ranging from the size of your fingernail to as big as a serving platter. They crawl across the ocean floor in vast herds, their segmented bodies protected by thick armor, their compound eyes scanning for food and danger. Above them swim the nautiloids, ancient relatives of modern squids and octopuses, but these things are enormous. Some species have shells 15 feet long, straight as spears, propelling themselves through the water like living torpedoes. They're the apex predators of this world, the T-Rexes of the Ordovician seas, hunting anything they can catch with tentacles that dart out from their massive shells. The seafloor itself is covered with gardens, not plants, but animals. Crinoids, sometimes called sea lilies, though they're actually animals related to starfish. They grow in dense forests, their feathery arms filtering microscopic food from the water, swaying in the currents like strange underwater flowers. Millions of them covering the continental shelves, creating ecosystems more diverse than anything on land would be for hundreds of millions of years. And everywhere, in every available niche, life has found a way to thrive. Graptolites floating in colonies, creating vast living nets that drift with the currents. Brachiopods covering rocks like barnacles, filtering water through their shells. Primitive fish just beginning to evolve, still jawless, still experimental, not yet the dominant force they would become. This is Earth's first truly complex ecosystem. After billions of years of single-celled organisms and simple multicellular life, evolution has finally cracked the code. It's figured out how to build elaborate body plans, develop specialized organs, create predator-prey relationships that drive increasing sophistication. The oceans are warm, carbon dioxide levels are high, sea levels are at some of the highest points in Earth's history. Shallow seas cover vast areas of the continents, creating massive platforms where marine life explodes in diversity. There are more different types of marine creatures now than there have ever been before. Life isn't just surviving anymore, it's flourishing, experimenting, filling every possible ecological role, and then without warning everything starts to die. It begins subtly. Ocean temperatures start dropping. Not everywhere at once, not catastrophically at first, but steadily, year by year, century by century. The warm currents that have circulated for millions of years begin to weaken. The shallow tropical seas start to cool. The trilobites notice first. These creatures have thrived in warm waters for tens of millions of years. Their entire physiology is optimized for tropical conditions. As temperatures drop just a few degrees, their metabolism slows, reproduction rates decline, eggs that should hatch don't, juveniles that should reach maturity die before reproducing. But the real killer isn't the cold itself, it's what the cold is doing to the ocean. Far to the south, on the ancient supercontinent Gondwana, something unprecedented is happening. Ice is forming, not just winter ice that melts in. Spring, but permanent glaciers. Year after year, snow falls on the southern highlands and doesn't melt. It accumulates, compresses, turns to ice. The ice spreads, flows downhill, begins covering larger and larger areas. This is Earth's first major ice age since complex life evolved, and it's about to get much worse. As the ice sheets grow, they lock up enormous quantities of water. Water that used to be in the oceans is now frozen on land, trapped in glaciers that are growing larger every century. And when you remove water from the ocean, sea levels fall. They don't just fall a little. Over a few 100,000 years, which is basically instantaneous in geological terms, sea levels drop by as much as 300 feet, maybe more, enough to completely drain those shallow continental shelf seas where most marine life has evolved. Imagine you're a trilobite living in one of these shallow seas. For your entire species' existence, spanning millions of years, this has been perfect habitat. Warm, shallow water, plenty of food, stable conditions. Then, within just a few generations, the water starts receding. The sea floor you crawl across begins emerging above the waves. The area you can live in shrinks by 90%, then 95%, then 99%. You're forced into deeper water, colder water, environments you're not adapted for, and you're not alone. Every species that lived in the shallows is being compressed into a smaller and smaller area. Competition becomes intense. Predators are everywhere because prey is concentrated. Food sources collapse because the shallow water organisms they depend on have vanished. Within a few 100,000 years, 60% of all marine genera disappear. Not just individual species, but entire groups of organisms, whole branches of the tree of life, gone forever. But here's where it gets truly terrifying. Just when survivors begin adapting to the new conditions, just when the remaining species start figuring out how to live in this colder, deeper ocean world, the ice melts. It happens fast. Whatever triggered the glaciation, some shift in ocean currents, some change in atmospheric composition, it reverses. The southern hemisphere warms. The massive ice sheets that took hundreds of thousands of years to build collapse in a geological instant. All that locked-up water floods back into the oceans. Sea levels rise rapidly, covering the continental shelves again, but now the water is different. It's full of nutrients washed off the newly flooded land. Algae blooms explode. These blooms die, sink to the bottom, and their decomposition sucks oxygen out of the water. The survivors of the first extinction pulse now face dead zones, vast areas of ocean where there's not enough oxygen to support complex life. Fish and trilobites swimming into these zones simply suffocate. Species that had managed to adapt to the cold and the changed sea levels now have to deal with anoxia, toxic conditions, rapid environmental shifts that give evolution. No time to respond. This second pulse finishes what the first one started. When the killing finally stops, 85% of all marine species are extinct. Entire groups of organisms that had dominated the oceans for tens of millions of years are completely wiped out. The great nautiloid predators, gone. Most trilobite families extinct. The graptolite colonies that had filled the open ocean vanished. But what caused this? What triggered the glaciation that set off this cascade of death? The most popular theory is simply that Gondwana drifted over the South Pole. When a large landmass sits at high latitude, ice accumulates. This creates a feedback loop. Ice reflects sunlight, which causes more cooling, which causes more ice formation. The whole planet cools. Sea levels drop, mass extinction begins. But some scientists think something else happened first, something that made the glaciation possible. There's a hypothesis, still debated, still controversial, that Earth was hit by a gamma-ray burst. These are the most energetic events in the universe, created when massive stars collapse into black holes. If one occurred close enough to Earth, within a few thousand light years, the burst of high-energy radiation would strip away part of our ozone layer. Without ozone protection, ultraviolet radiation from the sun would pour through the atmosphere. It wouldn't just kill organisms on land, remember. There's nothing on land yet. But UV radiation penetrates shallow water. It would kill phytoplankton, the microscopic organisms at the base of the entire marine food web. It would trigger mutations, damage DNA, cause widespread ecosystem collapse. And here's the kicker. Without as many organisms in the ocean absorbing carbon dioxide, atmospheric CO2 levels would drop. This could trigger cooling, glaciation, the whole extinction cascade. The gamma-ray burst wouldn't directly cause the mass extinction, it would just tip the first domino. The evidence for this is circumstantial. Some Ordovician rocks show signs of extensive UV damage to spores, but spores on land at this time were probably from primitive algae or fungus, and proving they died from a gamma-ray burst hundreds of millions of years later is nearly impossible. What we know for certain is that something triggered rapid glaciation, and that glaciation nearly emptied the oceans of complex life. But nearly isn't the same as completely. Some creatures survived, not by being stronger or faster, but by being adaptable. Some trilobite species that could tolerate colder water made it through. Some nautiloids that could hunt in deeper oceans survived. Brachiopods that could live in low oxygen conditions persisted in refuges where others suffocated. And some creatures thrived. The primitive jawless fish that had been minor players in the Ordovician ecosystem found themselves in a world with far less competition. The nautiloid predators that had kept fish populations in check were mostly gone. The ecological niches were empty, waiting to be filled. Over the next 50 million years, fish exploded in diversity. They developed jaws, teeth, better fins, more efficient body plans. The survivors of the Ordovician extinction became the ancestors of the fish that would eventually crawl onto land and become the first terrestrial vertebrates. Without the extinction, the oceans might have remained dominated by trilobites and nautiloids forever. Evolution had no reason to favour fish when other creatures were already successfully filling every available role. But the extinction reset the board. It cleared away the established players and gave the underdogs a chance. This is what mass extinctions do. They don't just kill, they create opportunity. They allow new forms of life to experiment, to evolve, to try strategies that would have failed in a world already full of successful competitors. The Ordovician-Silurian extinction was Earth's first great reset. The first time the planet wiped the slate clean and forced life to start over. It wouldn't be the last, not even close. Picture Earth 375 million years ago. If you could stand on a Devonian shoreline, you'd witness something unprecedented in our planet's history. Behind you, the world's first forests. Not the towering oaks and pines you know, but strange tree-like plants called Archaeopteris, reaching heights of 30 meters, casting shadows across landscapes that had been barren rock for billions of years. And before you, the ocean, teeming with an explosion of life so diverse, so abundant, that this era would forever be known as the Age of Fishes. The water is alive with creatures that would seem alien to modern eyes. Massive armoured fish called placoderms, some growing to 6 meters long, their heads encased in bony plates like medieval knights. Primitive sharks cruising through coral reefs that stretch for thousands of miles. Ammonites spiralling through the water column, their chambered shells catching the light. And in the shallows, something revolutionary. The first tetrapods, four-limbed vertebrates just beginning to haul themselves onto land, taking their first tentative steps in a journey that would eventually lead to dinosaurs, mammals, and you. This was a world flourishing. Life had recovered spectacularly from the Ordovician extinction 70 million years earlier. The oceans had refilled with diversity. The land was finally being colonized by complex plants. Everything pointed toward an accelerating explosion of biological complexity. The future looked bright. Then, over the span of 20 million years, 75% of all species vanished. Not in a single catastrophic moment like the Ordovician freezing, but through a series of devastating pulses, each one pushing life to the brink, allowing brief recovery, then striking again. This wasn't a quick death. This was prolonged agony, a slow suffocation that played out over timeframes almost impossible for human minds to comprehend. The late Devonian extinction wasn't one event. It was a cascade, a series of interconnected disasters that fed on each other, creating feedback loops that amplified the devastation. Scientists have identified at least 7 major extinction pulses during this period, each one wiping out significant percentages of marine life. The 2 biggest pulses, the Kellwasser events around 375 million years ago and the Hangenberg event around 359 million years ago, were particularly catastrophic. Here's what made this extinction uniquely terrible. It was an oxygen crisis. But not like the Ordovician, where the problem was cold water holding too much oxygen in the deep ocean. This time, vast stretches of the ocean were losing their oxygen entirely, becoming what scientists call anoxic zones, dead zones where nothing could breathe, nothing could survive. Imagine you're a placoderm, one of those massive armoured fish that rule the Devonian seas. You've been swimming these waters for your entire life, feeding on smaller fish, navigating by instinct through familiar territory. Then one day, you notice something wrong. The water tastes different. Your gills are working harder, pulling in water but extracting less oxygen. You swim toward the surface, seeking relief, but it doesn't help. The oxygen isn't just scarce at depth, it's disappearing throughout the entire water column. Other fish are around you, all showing the same distress. Gasping, swimming erratically, some floating belly up. The reef below, usually vibrant with colour and movement, is silent. Corals, normally filtering water with thousands of tiny polyps, have retracted. Sponges that would normally be pumping water through their bodies have shut down. The entire ecosystem is suffocating together. You survive this event. Barely. You find a pocket of better water closer to shore, where waves mixing with the atmosphere provide just enough oxygen to keep you alive. But the reef doesn't survive. Those corals that took millions of years to build their massive structures, they're dying en masse. Their skeletons will remain, ghostly monuments to lost ecosystems, but the living tissue, the polyps that built them, they're gone. And then, just as you think the crisis is over, just as oxygen levels start returning to normal, it happens again. Another pulse of anoxia, another wave of death sweeping through the oceans. This pattern repeated for 20 million years. Recovery, collapse, recovery, collapse. Each time more species disappeared, each time the ecosystems became simpler, less diverse, less resilient. But what was causing these oxygen crashes? This is where the story gets really interesting, because the answer might be above the water, not below it. Remember those first forests I mentioned? Those Archaeopteris trees spreading across previously barren continents? They were changing everything. For billions of years, Earth's land surfaces had been essentially lifeless rock. Some bacteria, maybe primitive mosses in wet areas, but nothing substantial. Then came the Devonian plant revolution, real roots penetrating deep into soil, real leaves capturing sunlight, real trees creating the first true forests in Earth's history. This seems like it should be good news, right? More plants mean more photosynthesis, more oxygen, more food for the base of the food chain, but evolution doesn't always work out neatly. Those first forests were doing something unprecedented to the planet's chemistry, and they were doing it on a massive scale. Trees have roots, deep roots that break apart rock, creating soil. But they're not just passively sitting there. They're actively dissolving minerals from the rock, pulling out nutrients they need to grow. This process, called chemical weathering, releases massive amounts of nutrients into the environment. And where do those nutrients go? Into rivers, and from rivers into the ocean. Now imagine this happening across every continent simultaneously. Millions of years of accumulated rock dust and dissolved minerals washing into the seas. The oceans are suddenly getting an enormous influx of nutrients, particularly phosphorus and nitrogen, the very elements that limit how much life can exist in water. In the modern world, we call this eutrophication. It happens when agricultural runoff or sewage dumps excess nutrients into lakes or coastal waters. At first it seems great. Algae blooms explode, turning the water green with life. But then those algae die. They sink to the bottom, where bacteria decompose them, and that decomposition consumes oxygen. Lots of oxygen. Scale that process up to planetary levels, and you get what happened in the late Devonian. Massive algae blooms fertilized by nutrient runoff from the first forests. Then massive die-offs as those blooms collapsed. Then bacterial decomposition consuming oxygen faster than it could be replenished, creating anoxic zones that spread across thousands of miles of ocean floor. The reef ecosystems were particularly vulnerable. Corals need clear, clean, oxygen-rich water. They can't survive algae blooms blocking the sunlight. They can't tolerate low oxygen levels, and they definitely can't handle the chemical changes that come with anoxic conditions. The Great Devonian reefs, structures that had taken millions of years to build, collapsed over the span of a few thousand years. And here's the truly staggering part. After the late Devonian extinction, reef ecosystems essentially disappeared for 100 million years. Think about that time frame. 100 million years. That's longer than the entire age of dinosaurs, longer than the span from the first mammals to today. For 100 million years, the oceans had no significant reefs, no massive carbonate structures built by coral colonies. The ecological niche was simply gone, wiped clean. But the forest nutrient hypothesis isn't the only explanation scientists have proposed. Some evidence points to volcanic activity, massive eruptions in what's now Siberia, releasing toxic gases and ash into the atmosphere. Others suggest asteroid impacts. At least 2 impact craters have been dated to the late Devonian period, though whether they caused the extinctions or merely coincided with them remains unclear. The truth is probably all of the above. A perfect storm of environmental stresses. Volcanic eruptions pumping carbon dioxide and sulfur into the atmosphere, changing the climate. Forests altering the chemistry of runoff entering the oceans. Possible asteroid impacts delivering additional shocks to already stressed ecosystems. And each of these factors amplifying the others, creating feedback loops that push the planet into repeated crises. Some researchers have even proposed that the forests themselves might have cooled the planet too effectively. By pulling carbon dioxide out of the atmosphere through photosynthesis and chemical weathering, They could have triggered periods of global cooling, and we know from the Ordovician extinction that rapid climate swings are deadly for marine life. But here's where the story takes a strange turn. While 75% of species were disappearing, while reef ecosystems were collapsing, while the oceans were suffocating, one particular group of creatures was doing just fine. Those early tetrapods, the first vertebrates learning to live on land, they were thriving. The late Devonian extinction was primarily a marine event. Life on land, still relatively simple and sparse, was less affected, and those first four-legged pioneers found themselves with new opportunities. As marine ecosystems collapsed, selection pressure favoured creatures that could survive in oxygen-poor water, or, better yet, spend more time on land where oxygen was abundant. The tetrapods that made it through the late Devonian weren't just survivors. They were the ancestors of every land vertebrate that would follow, every amphibian, reptile, bird and mammal, every dinosaur that would walk the earth, every human who would one day look back and try to understand what happened during those dark 20 million years. In a sense, the late Devonian extinction was the disaster that made us possible. If reef ecosystems had remained dominant, if the oceans had stayed rich and oxygen-filled, marine life might have remained the pinnacle of evolution. But the prolonged oxygen crisis changed the rules. It made land the safer option, the place with a future. By the end of the Hangenberg event around 359 million years ago, the world was transformed. The age of armoured fish was over. The great reefs were gone. The oceans were simpler, quieter, emptier. But on land, in the shadows of those world-changing forests, tetrapods were diversifying, adapting, preparing for the next chapter in Earth's story. They didn't know it, but they were inheriting the planet. And in another 100 million years, their descendants would dominate ecosystems that the Devonian fish could never have imagined. But Earth wasn't done resetting itself, not even close. The next extinction would make the late Devonian look like a minor setback. It would be so devastating, so thorough, so absolutely catastrophic that it would earn a name that still sends chills through anyone who studies Earth's history. They call it the Great Dying. Picture Earth 252 million years ago. Not the Earth you know with its familiar continents scattered across blue oceans. This was a completely different planet. All the land masses had crashed together into one colossal supercontinent called Pangaea. From pole to pole, from the eastern shore to the western coast, you could theoretically walk across the entire world without ever getting your feet wet. And it was dying. Not slowly, not gradually. This was death on a scale that makes every other extinction event look like a warm-up. By the time it was over, 96% of all species in the ocean would be gone. 70% of all species on land would be extinct. Entire ecosystems would vanish so completely that we barely have fossil evidence they ever existed. This wasn't a reset. This was nearly a complete shutdown. Earth came closer to becoming a sterile rock than at any other point in its history. We call it the Permian-Triassic extinction, but the geologists who study it have another name for it: the Great Dying. Here's what makes this so terrifying. It wasn't caused by an asteroid. No giant space rock slamming into the planet. No single catastrophic impact that you could point to and say, that's what did it. This was something worse. Something that came from within the Earth itself. Something that, once it started, couldn't be stopped. The Permian period had been relatively good times for life on Earth. The oceans were full of bizarre creatures. Trilobites, those armoured arthropods that had survived for 300 million years, were still crawling across the sea floor. Massive reefs built by strange organisms called rugose corals stretched for thousands of miles. The seas teemed with fish, sharks, and enormous nautiloids, squid-like predators that grew up to 20 feet long. On land, things were even weirder. The ancestors of mammals were the dominant vertebrates, not dinosaurs. Those wouldn't evolve for millions of years. Instead, you had creatures like gorgonopsids, saber-toothed predators that looked like a nightmare crossed between a lion and a reptile. Huge herbivores the size of hippos browsed on the tough vegetation. Insects buzzed through forests of primitive conifers and seed ferns. Life had conquered the land completely, spreading across Pangaea in all its strange and wonderful forms. Then, in what is now Siberia, the ground began to crack open. Not just a few volcanoes, not a single eruption. An area roughly the size of Europe started bleeding magma. Fissures hundreds of miles long opened up, pouring out lava in quantities that defy comprehension. Over the course of 1,000,000 years, maybe less, these Siberian traps, as they're now called, would vomit out enough lava to cover the entire United States in a layer of rock 500 feet thick. Think about that for a moment. 1,000,000 years sounds like a long time, and it is from a human perspective. But geologically it's nothing. It's instantaneous. And for every year of that 1,000,000-year eruption, massive amounts of lava were flooding across the landscape, burying everything in its path, turning forests into charcoal, boiling rivers, creating a vision of hell that would have impressed Dante. But the lava wasn't even the main problem. What killed the planet was what came with it. Every time magma forces its way to the surface, it brings gases with it. Carbon dioxide, sulfur dioxide, hydrogen chloride, all the volatile compounds that have been dissolved in the molten rock deep underground. During a normal volcanic eruption, you get a temporary spike in these gases, enough to affect local climate maybe, to cause some acid rain in the immediate area. Then it's over. The volcano goes dormant, and the Earth's natural systems absorb and neutralize the gases over a few years or decades. The Siberian traps erupted for 1,000,000 years. The gases didn't have time to be absorbed. They just kept accumulating, kept building up in the atmosphere, kept pushing Earth's climate further and further beyond any stable state. The sulfur dioxide hit first. Within years of the initial eruptions, it was combining with water vapor in the atmosphere to create sulfuric acid. Not in some laboratory, in the sky. Clouds became weapons. When it rained, it was acid rain so corrosive it could strip leaves off trees, kill fish in lakes and rivers, dissolve the shells of marine organisms. The oceans along the coast began turning acidic, making it impossible for anything with a calcium carbonate shell to survive. Entire reef systems began dissolving, literally melting into the increasingly hostile water. But that was just the beginning. The eruptions were so massive, so violent, that they were injecting chemicals directly into the stratosphere. Up there, 10 miles above the surface, sulfur compounds began reacting with ozone, destroying the protective layer that shields life from the sun's ultraviolet radiation. Within a few thousand years, large portions of the ozone layer had been stripped away. Now the sun itself became deadly. UV radiation intense enough to cause mutations, to burn through skin and leaf tissue, to damage DNA directly. Life that had evolved in the shade of a protective atmosphere suddenly found itself exposed to sterilizing radiation. And then came the carbon dioxide. Billions of tons of it, released year after year, century after century. At first the ocean absorbed a lot of it, but that just made the ocean acidification worse. Eventually, the oceans became saturated. They couldn't absorb anymore. The CO2 began accumulating in the atmosphere, building up, creating a greenhouse effect that pushed global temperatures higher and higher. The best estimates suggest that global average temperatures rose by 10 to 15 degrees Celsius. That might not sound like much, but remember, this is the global average. Near the equator, temperatures probably exceeded 50 degrees Celsius, 122 degrees Fahrenheit, in the shade. The interior of Pangaea became essentially uninhabitable. a dead zone where daytime temperatures were hot enough to kill anything that couldn't find deep caves or underground refuges. But even if you could survive the heat, you still had to breathe, and this is where things got truly apocalyptic. As the oceans warmed, something terrible began happening in the deep water. For hundreds of millions of years, ocean currents had been cycling cold, oxygen-rich water from the poles down to the deep sea, keeping even the deepest parts of the ocean oxygenated. But now, with temperatures skyrocketing, that circulation began to break down. The deep oceans became stagnant. Without oxygen, anaerobic bacteria took over. These bacteria don't breathe oxygen. They breathe sulfur compounds, and their waste product is hydrogen sulfide, poison gas. The same stuff that smells like rotten eggs, but in concentrations that are lethal to almost everything else. The deep oceans began filling with hydrogen sulfide, and then it started bubbling up to the surface. Within a few thousand years, massive blooms of sulfur bacteria had turned large portions of the ocean purple. Not a healthy colour. This was the colour of death. The hydrogen sulfide didn't stay in the water. It began escaping into the atmosphere. Coastal areas were poisoned. Animals that came to drink from rivers or the ocean were killed. The gas rose into the atmosphere, where it further damaged the ozone layer, creating a feedback loop of destruction. Marine life died in staggering numbers. The trilobites, those resilient creatures that had survived every previous extinction event, finally went extinct, every single species gone. The great reefs collapsed completely, leaving nothing but rubble on the seafloor. Fish died en masse. The fossil record shows evidence of mass mortality events where millions of fish suffocated simultaneously as the water turned anoxic. On land, it wasn't much better. The forests died first. Between the heat, the acid rain, and the UV radiation, trees simply couldn't cope. Whole forests turned to dead wood, standing tinder waiting for lightning strikes. When fires started, they burned for years, creating massive firestorms that consumed entire regions. The ash from these fires is preserved in rock layers all over the world, a testament to the scale of the destruction. With the forests gone, the herbivores had nothing to eat. They died. With the herbivores gone, the predators had nothing to hunt. They died too. Within a few thousand years, maybe as little as 60,000 years, the land was essentially empty. Oh, there were survivors, but they were tiny. Little lizard-like creatures hiding in burrows, small omnivores that could eat anything, insects, though even they suffered massive losses, and fungi. The fungi loved it. For millions of years after the main extinction event, the fossil record shows an unusual spike in fungal remains. Dead wood everywhere, dead animals everywhere, and fungi specialized in breaking down dead organic matter. For a brief geological moment, Earth became a planet of mushrooms, growing on the corpses of the world that had been. The recovery took 10 million years. Let that sink in. Not thousands of years, not hundreds of thousands. 10 million years before biodiversity began to return to pre-extinction levels. 10 million years before complex ecosystems re-established themselves. That's longer than the entire history of hominids on Earth. Longer than the gap between us and the common ancestor we share with chimpanzees. But when life did recover, it came back different. The old dominant groups, the mammal-like reptiles that had ruled the Permian, never fully recovered. They hung on for a while, but they'd lost their edge. New groups began to rise. Archosaurs, the ancestors of dinosaurs and crocodiles. These were the groups that would come to dominate the Triassic period. Eventually, some of these archosaurs would evolve into the dinosaurs, and they would rule the world for 165 million years. The Permian-Triassic extinction didn't just reset life on Earth, it completely reordered it. It determined which groups would dominate for the next 200 million years. Without the Great Dying, there probably would have been no dinosaurs, no T-Rex, no Brontosaurus, no Velociraptor. Earth would have remained a planet of mammal-like reptiles. But here's what should keep us awake at night. The Permian-Triassic extinction was caused by volcanic eruptions releasing greenhouse gases. Massive releases, yes, but spread over 1 million years. Current human activities are releasing greenhouse gases at a rate that's actually comparable to the Siberian traps, but compressed into centuries instead of millennia. We're running the same experiment, just faster. The Great Dying shows us what happens when you push a planetary climate system past certain tipping points. Ocean acidification, oxygen depletion, runaway greenhouse effects. We're seeing early signs of all of these today. We haven't reached Permian-Triassic levels, not even close, but we're headed in that direction. And the Permian-Triassic tells us that once you cross certain thresholds, the system can spiral out of control in ways that are nearly impossible to stop. 252 million years ago, Earth nearly died. Life survived, but just barely. It took millions of years to recover, and when it did, the world that emerged was completely different from the world that had been. The Great Dying reminds us that planets can break, that there are limits to what living systems can tolerate, that once you push hard enough, the Earth doesn't just reset, it nearly shuts down completely. Picture the world 201 million years ago. Not the dinosaur paradise you're probably imagining, but something much stranger. A world where dinosaurs existed, yes, but they weren't the dominant life forms, not even close. They were just another group of reptiles trying to make it in a crowded, competitive ecosystem. And honestly, they weren't winning. The real rulers of the Triassic world were creatures you've probably never heard of. Massive crocodile-like animals called crurotarsans. Some walked on 4 legs like modern crocodiles, but others, the really successful ones, walked upright on 2 legs like dinosaurs. They had similar body plans, similar hunting strategies, similar ecological roles. In every practical sense, they were doing everything dinosaurs could do, but doing it better. There were herbivorous crurotarsans that looked remarkably like the horned dinosaurs that would come later. There were predatory ones that hunted in packs. Some reached lengths of 20 feet and could take down prey several times their size. They had efficient metabolisms, sophisticated social behaviors, and they'd been perfecting their survival strategies for tens of millions of years. The dinosaurs were the underdogs, the evolutionary also-rans, stuck in marginal niches while their crocodile-like cousins dominated the planet. And it wasn't just crurotarsans. The Triassic had other dominant groups. Enormous amphibians still lurked in rivers and lakes, some growing to 15 feet long. Early mammal relatives called cynodonts prowled the underbrush, many of them surprisingly large and successful. Flying reptiles called pterosaurs had already taken to the skies. The oceans were full of massive marine reptiles, ichthyosaurs and nothosaurs, that made modern great white sharks look timid. In this crowded world, dinosaurs occupied a handful of ecological roles. They were mostly small to medium-sized animals. Some were herbivores, some were predators, but none were dominant. If you could have surveyed the Triassic landscape and tried to predict which animal group would inherit the Earth, you would never have picked dinosaurs. They simply weren't special enough, weren't successful enough, weren't dominant enough. But evolution doesn't care about who deserves to win. It only cares about who survives. And what happened next changed everything. Around 201 million years ago, Pangaea, the supercontinent that had dominated Earth's geography for 100 million years, began to break apart. This wasn't a gentle, gradual separation. This was violent, catastrophic, a tectonic divorce that would reshape the planet. As the Atlantic Ocean began forming, splitting what would become Africa and South America from North America, and Europe. Something unprecedented happened underground. Magma began rising through the fractures in Earth's crust, not from a single volcano, not even from a chain of volcanoes, but from thousands of fissures along a rupture zone that stretched for thousands of miles. This was the Central Atlantic Magmatic Province, or CAMP, and it would prove to be one of the largest volcanic events in Earth's history. Over the course of maybe 500,000 years, though the worst of it probably happened much faster, these eruptions poured out enough lava to cover an area the size of Europe several feet deep. Now, if you're thinking that's not so bad, remember what you learned from the Permian extinction. The lava itself wasn't the problem. The real killers were the gases. Those fissure eruptions release staggering amounts of carbon dioxide, sulfur dioxide, and other volatile compounds directly into the atmosphere. The chemical signature preserved in rocks from this period tells a story of environmental chaos that makes modern climate change look like a minor inconvenience. The first wave of killing came from sulfur dioxide. When it reached the upper atmosphere, it created aerosols that reflected sunlight back into space. Global temperatures plummeted. Some estimates suggest cooling of 5 to 10 degrees Celsius in just a few years. For animals adapted to the warm, relatively stable Triassic climate, this was catastrophic. But here's where it gets really diabolical. The sulfur aerosols only stayed in the atmosphere for a few years, maybe a decade. Then they rained out as sulfuric acid, devastating terrestrial and marine ecosystems. And once they were gone, all that carbon dioxide was still there, waiting. Global temperatures rebounded, but they didn't just return to normal, they shot past it. The CO2 created a greenhouse effect that raised temperatures 3 to 6 degrees above pre-eruption levels. So within maybe 20 or 30 years, the world went from normal to freezing to lethally hot. But it didn't stop there. The eruptions were episodic, coming in pulses separated by decades or centuries. Each new pulse meant another round of cooling followed by warming. Climate whiplash on a scale that makes the ice ages look gentle. Ocean chemistry went haywire. The carbon dioxide dissolved in seawater, creating carbonic acid and driving ocean acidification. Coral reefs, which had been slowly recovering since the Permian extinction, collapsed again. Marine ecosystems that depended on calcium carbonate, anything with shells or external skeletons, struggled to survive. The oxygen content of the oceans fluctuated wildly. Some regions became anoxic dead zones. Others experienced toxic algae blooms that poisoned the food chain from the bottom up. On land, plants faced an impossible challenge. The rapid temperature swings meant that survival strategies that worked one decade were lethal the next. Cold-adapted plants expanded during cooling phases only to be wiped out when temperatures spiked. Heat-tolerant species colonized new territories, then died en masse during the next cooling event. The fossil record from this period shows massive die-offs of plant species, followed by brief recoveries, followed by more die-offs. Forests that had stood for millions of years disappeared within generations. And the animals that depended on those plants, they were caught in a death spiral. Herbivores starved when vegetation collapsed. Predators starved when herbivores disappeared. Ecosystems that had been stable for tens of millions of years unraveled in what was, geologically speaking, the blink of an eye. Some researchers think the worst of the extinction happened in less than 10,000 years. Others think it might have been even faster, possibly just a few thousand years for the main killing event. When the dust settled, or rather, when the volcanic gases finally cleared and the climate stabilized, about 80% of all species were gone. But here's what's fascinating. The extinction was incredibly selective. It didn't kill everything equally. It picked winners and losers in ways that seem almost random, until you look closely at the survival patterns. The Crurotarsans, those successful crocodile-like archosaurs that had dominated the Triassic, nearly wiped out. A few small species survived, and their descendants eventually became modern crocodiles and alligators, relegated to rivers and swamps. But the giant terrestrial species, the ones that had outcompeted dinosaurs for tens of millions of years, all gone. The large amphibians, extinct. Most of the mammal-like cynodonts, dead. Many marine reptile groups, vanished. But dinosaurs, they made it through. Not all of them, certainly. Many dinosaur species went extinct during the crisis, but enough survived to repopulate the planet. And here's the critical question. Why? What did dinosaurs have that Crurotarsans didn't? Why did the underdog survive while the dominant groups perished? The answer seems to be related to metabolic efficiency and dietary flexibility. Recent research suggests that many early dinosaurs had more efficient respiratory systems than their competitors. They had evolved air sacs, similar to modern birds, that allowed them to extract more oxygen from each breath. In a world where oxygen levels were fluctuating and temperatures were swinging wildly, this efficiency advantage might have been the difference between survival and extinction. Dinosaurs also seem to have been more generalist feeders than many of their competitors. The Crurotarsans had specialized, optimized for specific prey and specific hunting strategies. When ecosystems collapsed, their food sources disappeared and they couldn't adapt quickly enough. Many dinosaurs, particularly the early ones that survived the extinction, were more opportunistic. They could switch between different food sources, adjust their hunting strategies, survive on less. Size played a role too. Many of the dinosaurs that made it through were relatively small, less than 30 feet long, with lower food requirements than the massive Crurotarsans. In a world where food was scarce and unpredictable, being smaller and more efficient was an advantage. But perhaps most importantly, dinosaurs got lucky. And in mass extinctions, luck matters as much as adaptation. The specific regions where dinosaurs had their strongest populations happened to be areas where refugia, small pockets of relatively stable climate, persisted during the worst of the crisis. Some Crurotarsan populations weren't so fortunate. They lived in regions where temperature swings were most extreme, where vegetation collapse was most complete. This is one of the hard truths about mass extinctions. They're not entirely fair. They don't always favour the best adapted or the most successful. Sometimes they favour the lucky, the groups that happen to be in the right place at the right time with just enough of the right adaptations to squeak through. When the climate finally stabilised around 200 million years ago, the world that emerged was radically different from the one that had existed before. The ecological vacuum left by extinct Crurotarsans and other groups was enormous, and dinosaurs, those former underdogs, were perfectly positioned to fill it. They diversified explosively. Within a few million years, dinosaurs had evolved into the massive long-necked sauropods, the armoured stegosaurs, the predatory theropods that would eventually produce species like Allosaurus and Tyrannosaurus rex. They spread across every continent, adapted to every terrestrial environment, and grew to sizes that still boggle the mind today. For the next 135 million years, dinosaurs would be the dominant large animals on land. The Triassic-Jurassic extinction had handed them the planet, not because they were superior, but because they survived when others didn't, because they were efficient enough, flexible enough, and lucky enough to make it through the crisis. But there's a deeper lesson here. Dominance is temporary. Success is no guarantee of survival. The Crurotarsans had ruled for tens of millions of years, perfectly adapted to their world. Then the world changed, and adaptation didn't matter. The extinction didn't care about their evolutionary achievements or their ecological success. It only cared about who could survive rapid environmental change. The dinosaurs inherited an empty planet and made it their own. But their reign wouldn't last forever. 135 million years later, they would face their own reset. And when it came, they would learn what the Crurotarsans had learned, that no matter how successful you become, no matter how well adapted you are, Earth always keeps one more catastrophe in reserve. Picture a spring morning 66 million years ago. The sun rises over what will one day be the Yucatan Peninsula, but today it's a shallow, tropical sea. The water is warm, crystal clear, teeming with ammonites and ancient fish. On the shores, flowering plants, a relatively new invention of evolution, bloom in colours the world has rarely seen before. Insects hum between the flowers. Birds, descendants of earlier dinosaurs, sing from the trees. Inland, across the vast forests and plains of late Cretaceous Earth, the dinosaurs rule. And not just rule, they thrive. This isn't the twilight of the dinosaur age. This is their golden hour. Tyrannosaurus rex stalks through the forests of what will become North America, the apex predator of a sophisticated ecosystem. Triceratops herds migrate across seasonal grasslands, following the rains. In South America, the massive titanosaurs, the largest animals ever to walk on land, strip leaves from trees 40 feet above the ground. The dinosaurs have been the dominant land animals for 165 million years. For context, humans have only existed for about 300,000 years. The dinosaurs had already been running the planet for over 500 times longer than we've existed. They're not declining. They're not struggling. They're at the height of their evolutionary success, diversifying into new forms, adapting to new environments, spreading into every available ecological niche. Then, in a single morning, everything ends. At 10:47 a.m., give or take a few minutes, because who's really keeping time, a rock from space hits the shallow sea off the Yucatan. It's been travelling through the solar system for billions of years, an asteroid 10 kilometres wide, roughly the height of Mount Everest. It's been falling toward Earth for months, maybe years, growing brighter in the sky night by night. Some dinosaurs might have noticed it, that increasingly bright star that never moved with the others, but they had no concept of what it meant. The asteroid hits the ocean at 20 kilometres per second. That's 45,000 miles per hour. At that speed, air can't get out of the way fast enough. It compresses in front of the asteroid until it becomes a plasma, hotter than the surface of the sun. The rock itself doesn't slow down. It doesn't splash into the water. It punches through the ocean like the ocean isn't even there, vaporizing millions of gallons of seawater instantly, and slams into the limestone bedrock below. The impact releases the energy of approximately 10 billion Hiroshima bombs, all at once, in a single point. Within microseconds, a crater 20 kilometers deep and 100 kilometers wide explodes into existence. Rock that has been solid for hundreds of millions of years simply ceases to exist, converted to plasma and vapor. The bedrock underneath, compressed beyond anything possible under normal conditions, rebounds like a springboard, creating a peak in the center of the crater that rises 10 kilometers high before collapsing. The energy from the impact has to go somewhere. It radiates outward in every direction at once. Within seconds, everything within 1,000 kilometers is simply obliterated. Not burned, not destroyed, obliterated, cease to exist. Any dinosaur, any tree, any living thing within that radius is reduced to its component atoms before its nervous system could even register that something happened. But that's just the beginning. The impact throws debris into the atmosphere, not just rocks, trillions of tons of vaporized rock, superheated to thousands of degrees. This material shoots upward faster than escape velocity. Within minutes, some of it is in space, but most of it arcs through the upper atmosphere and begins falling back to Earth. falling everywhere. Across North America, South America, Africa, Europe, Asia, glowing fragments of impact debris rain down like a second sun. The thermal radiation from this debris is intense enough to ignite organic material across entire continents. Forests that have stood for millions of years burst into flame, not just near the impact, everywhere. From Mexico to Montana, from California to the Carolinas, from the Amazon to the Arctic, everything combustible begins to burn. The world becomes a furnace. Dinosaurs that survived the initial impact, that were far enough away to escape the immediate blast, now face a global firestorm. Hadrosaurs, those peaceful plant-eaters, run in panic as the trees around them ignite. Tyrannosaurs, the apex predators who have never known fear, flee alongside their prey, both species united in terror. But there's nowhere to run. The fires are everywhere. The smoke fills the sky. The heat becomes unbearable. Within hours, the atmospheric temperature has risen by dozens of degrees globally. Many dinosaurs simply cook alive, even if they never see a flame. Meanwhile, the impact has triggered something else. The energy transferred to the Earth's crust sets off earthquakes worldwide. Magnitude 10, magnitude 11, scales of seismic activity that wouldn't be seen again for 66 million years. In the Gulf of Mexico, the ocean floor itself ripples like water. Tsunami waves 300 meters high radiate outward from the impact site. They cross the Gulf of Mexico in less than an hour, slamming into what will one day be Texas and Louisiana, with the force of mountains made of water. They race across the Atlantic, reaching Africa within hours. No coastal ecosystem anywhere on Earth survives. The dinosaurs on the coasts, the ones who lived in the shallow seas and tidal zones, don't even get the dignity of a quick death. They're swept inland, tumbled through debris-filled water, drowned and crushed simultaneously. Their bodies are deposited miles from the sea, mixed with marine sediments and impact debris in a layer of rock that geologists will one day call the KPG boundary. Within 24 hours of impact, most large land animals are dead or dying. But the extinction event is just getting started. The debris in the atmosphere begins to settle, but there's so much of it. Trillions of tons of fine particulate matter, sulfur aerosols from vaporized limestone, soot from the global fires, all of it hangs in the air, blocking sunlight. Within weeks, the sky becomes dark, not night dark, perpetual twilight dark. The sun becomes a dim orange disk barely visible through the haze. Photosynthesis stops, not completely, not everywhere, but enough. Plants that depend on full sunlight begin to die. Within months, forests that survived the initial fires begin to collapse as trees exhaust their energy reserves and find no light to replenish them. The plant die-off cascades through the food chain. Herbivorous dinosaurs, already stressed by the heat and fires, now face starvation. They strip what vegetation remains, but it's not enough. The great herds thin. The magnificent titanosaurs, who need hundreds of pounds of plant matter daily, begin to fall. Their bodies lie where they collapse, too many for scavengers to consume. The carnivores do better at first. There's plenty of dead meat. Tyrannosaurs feed on carrion, something they probably did occasionally anyway, but now do exclusively. But the carrion doesn't last. Bodies rot, get consumed, or freeze in the cooling climate. Within a year, the carnivores face their own starvation. These apex predators, these kings of the Cretaceous, die slowly, their powerful bodies betraying them as their metabolism demands more food than the dying world can provide. The temperature is dropping now. With sunlight blocked, the Earth's surface begins to cool. What had been a global furnace becomes a global freezer. The impact winter has begun. This isn't like natural winter, this is years of constant darkness and cold. Temperatures in many regions drop by 25 degrees Celsius or more. Water freezes. What few plants managed to survive the fires and darkness now face months or years of freezing temperatures in regions that were tropical just months before. And there's another factor making everything worse. Halfway around the world from the impact site in what will one day be India, the Deccan Traps volcanic system has been erupting on and off for thousands of years. These aren't normal volcanoes. These are flood basalts, eruptions that pour lava across thousands of square kilometers, releasing massive amounts of carbon dioxide and sulfur dioxide into the atmosphere. Under normal circumstances, life could adapt to this. Species have survived similar eruptions before. But these aren't normal circumstances. The asteroid impact has stressed every ecosystem on Earth to the breaking point. The volcanic gases push many of them over the edge. Some researchers think the impact itself might have triggered increased volcanic activity, sending seismic shockwaves through the Earth's crust that intensified the Deccan eruptions. Others think it's just terrible timing, two separate disasters hitting the same planet within a few thousand years of each other. Either way, the combination is devastating. The 1-2 punch of impact winter followed by volcanic climate disruption ensures that the Earth's climate remains chaotic for thousands of years. By the time the dust finally settles, literally 75% of all species on Earth are gone. Not just the dinosaurs, ammonites, those beautiful spiral-shelled marine animals that had survived every previous extinction, finally go extinct. Most marine reptiles disappear. Pterosaurs, the flying reptiles, vanish completely. Many plant species, especially those dependent on specific pollinators or growing conditions, die out. Entire ecosystems collapse like houses of cards, but some things survive. And what survives tells us everything about what it takes to live through a global catastrophe. The survivors share certain characteristics. They're small. They can survive on very little food. Many of them can burrow underground or hide in water. They're generalists, capable of eating whatever they can find rather than specialists dependent on specific foods. They're cold-tolerant, capable of surviving temperature extremes. Most importantly, they can reproduce quickly, allowing them to recover faster when conditions improve. Mammals fit this profile perfectly. During the Cretaceous, mammals had been small, mostly nocturnal creatures living in the shadows of the dinosaurs. The largest was about the size of a raccoon. Most were mouse or rat-sized. They could burrow. They had fur for insulation. They were already adapted to cold nights. They could eat almost anything. Insects, plants, seeds, whatever they found. When the impact winter hit, these small furry survivors retreated underground, living off seeds and roots and insects, waiting out the darkness in burrows where the temperature stayed relatively stable. Birds survived too, though most bird species went extinct. The survivors were, again, small ground-dwelling species that could eat seeds and hide in vegetation or burrows. The large flightless birds, the specialized species that had adapted to specific ecosystems, they died. But the small, adaptable ones made it through. Crocodiles and turtles, those ancient reptile lineages, survived. They're cold-blooded, so they don't need as much food. They can brumate, entering a state of dormancy during cold or harsh conditions. They can eat carrion when necessary. Crocodiles can go months without eating. These traits, which might seem like disadvantages during normal times, became life-saving during the catastrophe. In the oceans, the survivors were similar. Small fish, generalist feeders, species that could live in deep water where the surface chaos mattered less. Sharks survived, those ancient predators whose basic body plan had already been working for hundreds of millions of years. Some marine mammals, early ancestors of whales, made it through. The coral reefs mostly died, but some corals survived in deeper water and would eventually recolonize the shallows. When the skies finally cleared, maybe 10 years after impact, maybe 100, the survivors emerged into a transformed world. The dominant life forms of the Cretaceous were gone. The age of dinosaurs was over. But for the survivors, this was an opportunity. With the dinosaurs gone, ecological niches stood empty. Forests began to recover, starting with fast-growing ferns and eventually rebuilding into complex ecosystems. And the mammals, those small furry survivors, began to diversify. Within a few million years, mammals would evolve into forms that would have been impossible while the dinosaurs lived. Some became large herbivores, filling the niches left by sauropods and hadrosaurs. Others became predators. Within 10 million years, some mammals were as large as bears. Within 25 million years, some were as large as elephants. The ancestors of whales returned to the sea. The ancestors of bats took to the air. And one small group of tree-dwelling mammals developed forward-facing eyes, grasping hands, and unusually large brains. They would eventually become primates, and much later, after many more millions of years of evolution, they would become us. We exist because a rock from space killed the dinosaurs. That's not speculation or theory. That's documented fact written in rock layers around the world. Without the Cretaceous-Paleogene extinction, mammals would still be small nocturnal creatures hiding from dinosaurs. There would be no primates, no humans, no civilization. The most catastrophic event in the last 100 million years created the conditions for our existence. But it also teaches us something terrifying. Earth's reset button can be pushed at any moment, and when it is, size and strength mean nothing. Dominance means nothing. What matters is adaptability, resilience, the ability to survive when everything goes wrong. The dinosaurs ruled for 165 million years and disappeared in decades. The question hanging over us now is simple. When Earth's next reset comes, will we be the dinosaurs or the mammals? Picture the planet right now, seen from far above. City lights glowing like constellations. Cargo ships crawling across the oceans like slow-moving insects. Highways glowing faintly in the dark, tracing out the veins of a very strange new ecosystem. Now zoom the camera down, into a rainforest that used to be continuous, green, uninterrupted horizon. Now sliced into fragments by roads, mines, plantations, into coral reefs that once looked like underwater cities of colour and life, now bleached white like bone, into grasslands turned to dust, wetlands drained to fields, rivers dammed into silent artificial lakes. Life is still everywhere. Birds still sing, trees still grow, fish still swim, but the numbers are different. If you could see species the way a geneticist does, as data points on a long timeline, you'd notice something deeply unsettling. The dots are disappearing. Fast. Scientists call it the extinction rate, the pace at which species vanish from the planet. Over the last 500 million years, during normal times between mass extinctions, that background rate has been relatively slow. Maybe one species out of every million disappearing each year, mostly replaced by the slow, patient work of evolution. But when researchers look at the last century or two, they see something else entirely. By every serious estimate, today's extinction rate is between 100 and 1,000 times higher than that long-term background. Some studies suggest it might even be more. Species that once numbered in the millions are now down to thousands. Others are already gone, known only from dusty museum drawers and fading photographs. And many are disappearing before we even notice they existed. Entire evolutionary lineages erased without even getting a name. To paleontologists, this pattern looks eerily familiar. A spike in extinctions, a rapid loss of biodiversity, ecosystems unravelling not over millions of years, but over centuries and decades. On geological timescales, that's instant. So the question hangs in the air like a quiet warning. Are we already living through Earth's sixth mass extinction? And if we are, what's driving it this time? In the past, the culprits were things like supervolcanoes, asteroid impacts, runaway climate shifts triggered by deep time tectonics, forces utterly beyond the control of any individual organism. This time, the main driver is a single species. Us. It didn't happen all at once. For most of human history, we were just clever animals, nudging ecosystems here and there, burning patches of forest to encourage game, hunting some species harder than others, spreading plants and animals along our trade routes. But as our population grew and our tools got sharper, our influence crossed an invisible threshold. What began as local changes started to merge, link and stack until they became something else entirely, a planetary scale force. Think of all the ways we reshape the world, often without meaning to. We clear forest for timber, cattle, soys, palm oil. Huge areas that once held a riot of species become simplified landscapes of one or two crops. We drain wetlands, straighten rivers, build dams and levees. Habitats that evolved over millions of years vanish in a few construction seasons. We burn fossil fuels, releasing carbon that had been stored underground since before the dinosaurs. The atmosphere thickens with greenhouse gases. The climate shifts faster than in most past natural events, pushing species out of the narrow ranges of temperature and rainfall they're adapted to. We fill the air and water with pollution, plastics that break into microscopic fragments, pesticides that drift on the wind, heavy metals washed into rivers, nitrogen from fertilizers creating dead zones in the sea. Each chemical, each compound, another small stress piled onto already stressed organisms. We hunt and fish with industrial efficiency. Vast nets rake the ocean floor. Factory ships process entire schools of fish in hours. Bushmeat hunting and wildlife trade empty forests of large mammals and birds. We move organisms around the world, accidentally and on purpose. Rats, cats, pigs, diseases, invasive plants and insects leap continents in the holds of ships and airplanes, outcompeting or devouring native species that have no defences. Any one of these forces might have been manageable on its own. Combined, they create something like the perfect storm, and some of the earliest, clearest signs that the storm is here come from a group of creatures most of us barely notice. Insects. For hundreds of millions of years, insects have been the quiet machinery of Earth's ecosystems, pollinating flowers, recycling dead matter, feeding birds, bats, reptiles, amphibians, fish, and countless other creatures. They are the gears and cogs that keep the living world turning. Now, in many places, those gears are grinding down. Long-term studies in Europe, North America, and elsewhere show insect populations dropping by 50%, 70%, sometimes more, over just a few decades. In some regions, the total biomass of flying insects has crashed by 3/4 or more. The insect apocalypse, some scientists call it. It doesn't look dramatic at first glance. No mushroom clouds, no tidal waves, just fewer bugs on the windshield than you remember from childhood. Quieter summer nights, fewer butterflies in the fields, fewer fireflies in the dark, but the consequences ripple outward. Fewer insects mean less food for birds. Songbirds that relied on insect-rich springs to feed their chicks now struggle. Their numbers fall. Bats lose their primary prey. Frogs and lizards go hungry. Pollinators vanish, and with them the plants that depended on them. It's like carefully removing screws from a plane in mid-flight. You might not notice a problem at first, but piece by piece, the structure weakens until one day something essential gives way. Meanwhile, beneath the surface of the oceans, another crisis is unfolding. One that echoes, in unsettling ways, the worst mass extinction in Earth's history, the Great Dying of the Permian Triassic. When we burn coal, oil and gas, the carbon dioxide doesn't just stay in the sky. A large fraction dissolves into the oceans. There, it reacts with seawater to form carbonic acid, lowering the pH of the water. Slowly, steadily, the seas grow more acidic. To us, the change is almost imperceptible. A small shift on a pH scale you might have last seen in a high school textbook. To marine life that builds shells and skeletons from calcium carbonate, it's a different story. As the water becomes more acidic, those minerals become harder to form, easier to dissolve, shells thin, coral skeletons weaken, larval shellfish struggle to survive their earliest, most vulnerable stages. Coral reefs, which support an extraordinary fraction of marine biodiversity, are hit with a double blow. Acidification from below and warming from above. When water gets too warm, corals expel the symbiotic algae that feed them, turning ghostly white. If the heat lasts too long, they die. In Earth's deep past, similar combinations of rapid carbon release, warming and ocean acidification drove several major extinction events. During the Great Dying, massive volcanic eruptions poured greenhouse gases into the atmosphere. Temperatures soared. The oceans turned acidic and in many regions oxygen poor. Up to 90% of marine species vanished. We are not there, not yet. But when geochemists compare the current rate of carbon release to those ancient events, they see uncomfortable parallels. In some ways, today's changes are even faster. So are we already in a sixth mass extinction? Here, the story becomes more complicated. On one side, many biologists argue that we've already crossed the threshold. They point to the spike in extinction rates, the widespread collapse of populations, the fragmentation of habitats, the accumulating signs of planetary-scale disruption. From their perspective, the sixth extinction isn't something that might happen in the future. It's already underway, unfolding all around us. On the other side, some scientists are more cautious. They agree that the trends are alarming, that we're digging a deep hole, but they note that, so far, the absolute number of documented extinctions is still lower than in the 5 great die-offs of the past. They argue that with rapid, coordinated action, we might still pull back from the brink, flatten the extinction curve before it becomes a true mass extinction in the strict geological sense. Part of the uncertainty comes from simple ignorance. We don't even know how many species exist on Earth. Estimates range from a few million to tens of millions. Many are small, hidden, poorly studied, insects, fungi, microbes in soil and deep ocean. They can disappear long before anyone notices. So it's possible that we're undercounting the losses, that the sixth extinction is further along than we think. It's also possible that some parts of the living world are more resilient than we fear, able to bounce back if we give them space and time. What's clear is that we are in a narrow window. We can still influence how severe this reset will be, how many branches of the tree of life are pruned, how long it will take for ecosystems to recover, if they ever truly do. And within this unfolding crisis, not all species face the same fate. The most vulnerable tend to share certain traits. They need very specific habitats that are now disappearing. Old-growth forests, coral reefs, intact wetlands. They have small ranges, maybe confined to a single island, mountain range, or river system. They reproduce slowly, have few offspring, invest heavily in each one. Large mammals, big birds, ancient trees, many reptiles and amphibians. These are the species evolution took its time with, polishing them for narrow niches. They shine like rare jewels in the ecological tapestry. But those same specializations make them fragile. Then there are the generalists, the opportunists, the species that can live almost anywhere, eat almost anything, adapt their behavior quickly. Rats, crows, pigeons, cockroaches, Certain weeds, certain fish, certain microbes, and of course, humans. These are the probable winners of a sixth extinction. They thrive in disturbed environments. They ride the wave of human expansion, slip into our cities, farms, landfills, ships, and sewers. If the future belongs to anyone, it may belong to them, and to whatever new forms evolve from their ranks in the ages to come. But that future is not entirely written. Unlike the trilobites of the Ordovician, the armoured fishes of the Devonian, or the ferns and reptiles of the Permian, one of the species now driving planetary change is also aware of what it's doing. It can measure extinction rates, model climate futures, map the shrinking ranges of endangered animals in real time. We can name what's happening, we can imagine alternative paths. We're both the asteroid and the only species that can choose to deflect it. Right now, somewhere in a rainforest fragment, a beetle that has never been catalogued is climbing a leaf in the dark. Somewhere on a reef, a tiny coral polyp is trying to build its first shell in slightly more acidic water. Somewhere in the soil, a fungus is weaving threads between roots, still doing the quiet work it has done since before humans existed. They're all playing their parts in a drama that stretches back nearly 4 billion years. Whether we are living through the opening act of a new mass extinction, or standing near the edge of a cliff we can still walk away from, that depends more than ever before on the choices of one recently evolved primate, us. And if the past 5 resets have taught Earth anything, it's this. Whatever happens next, the planet will eventually recover. Life will adapt, diversify and flourish again, though it may take millions of years. The real question is not whether Earth will survive the 6th extinction. It's whether we will be part of what comes after. Imagine zooming out from deep time, past the Ordovician seas, the Devonian swamps, the burning deserts of the Permian, the dinosaur forests of the Cretaceous, past the glaciers that nearly erased our own ancestors. Keep zooming out until the entire history of complex life on Earth is a thin film wrapped around a spinning rock. Now zoom back in, to a single century, ours. The other 5 great resets were written by geology and orbital mechanics. Slow shifts in continents, gradual build-ups of carbon dioxide, rare blind accidents from space. They were brutal, but they were simple. One big driver at a time, maybe 2. Climate shifts, volcanism, and impact. This time is different, because for the first time in 4.5 billion years, one species is pulling multiple extinction triggers at once. Your species. Right now, human activity is stacking the deck in a way no asteroid ever could. Think of the known killers from past extinctions, the old executioners of life, and line them up. Rapid climate warming, we're doing that. Ocean acidification, that too. Destruction of habitats on land and sea, every day. Runaway greenhouse gases from thawing permafrost and collapsing ecosystems. We've started that domino line as well. In previous mass extinctions, these forces showed up one at a time, or in slow cascade. This time, they're converging, interlocking, feeding on each other in feedback loops that even Earth's long memory has rarely seen. Take climate. In the Permian, it took tens of thousands of years for volcanic eruptions to pump enough carbon dioxide into the air to heat the planet by 5 or 6 degrees. That was enough to kill around 90% of marine species and most life on land. Today, humans have raised atmospheric CO2 faster than at any point in at least the last 3 million years. In about 150 years, we've done what used to take nature tens of millennia. The graph doesn't slope up, it spikes, almost vertical. Biology has a word for this: rate. Not just how much the world changes, but how fast. Life can survive astonishing transformations if they happen slowly enough. Forests migrate, species shift their ranges, evolution experiments, Winners and losers appear, but the web holds. But when change outruns adaptation, the web tears. Species that can't move quickly enough, can't change fast enough, simply disappear. Corals that need decades to grow die in a single heat wave. Trees that might have moved north over centuries can't uproot in time when the climate of Spain shows up in southern England within one human lifetime. This is the speed factor. The Ordovician seas cooled over hundreds of thousands of years. The late Devonian crisis unfolded in pulses over 20 million years. Even the asteroid that killed the dinosaurs landed on a planet already warmed by slower climate shifts. Our current disruption has gone from zero to global in less than 2 human generations. Most of the carbon that will shape the next 10,000 years was released by people whose grandparents were alive when horses still dominated city streets. The underlying physics hasn't changed, but the tempo has, and life is trying to sprint to keep up with a runaway freight train. Now layer on everything else. Deforestation is stripping away entire biomes that once buffered climate swings. Wetlands that used to store floodwaters and filter pollution are vanishing beneath concrete and crops. The oceans are filling with plastics, heavy metals, and industrial chemicals that didn't exist a century ago, and that no species has ever had to adapt to. Rivers are dammed, deserts are irrigated, mountains are mined from within. Nighttime itself is being erased by lights that rewrite the day-night cycles of insects, birds, even plants. This is no longer just climate change, it is planetary remodeling. And on top of these slow, grinding pressures, there are the single-moment triggers, the hammers hovering above the whack-a-mole board of civilization. Some are old. Supervolcanoes still simmer under places like Yellowstone and Toba, their magma chambers slowly filling. The odds of an eruption in any given year are low, but not zero. A single super-eruption could dump ash across continents, darken the sky, crash agriculture, and send global temperatures plunging for years. Asteroids still cross Earth's orbit. Our telescopes have found most of the really large ones, but not all. And smaller impactors, only a few hundred meters across, are still big enough to devastate entire regions and trigger global climate disruptions. These were always part of Earth's lottery. But others are new. They exist only because we do. Nuclear weapons, sitting in silos and submarines, quietly waiting for a few minutes of human error, miscommunication, or deliberate choice. A full-scale nuclear war would not look like the asteroid that ended the Cretaceous, but the effects could rhyme. Dust and soot lifted into the stratosphere, blocking sunlight, collapsing harvests. A nuclear winter layered on top of a warming world. Then there are the invisible digital threats, self-improving artificial intelligences built to optimize, predict, control. Tools that could transform medicine, science, and communication, but that could also be misaligned with human values or twisted into instruments of surveillance, manipulation, or war. Runaway AI might not melt ice caps or poison oceans directly, but it could accelerate the destruction, making resource extraction more efficient, misinformation more persuasive, weapons more precise. Or it could disrupt the fragile coordination needed to pull back from the brink, fracturing the global response exactly when a unified one is most needed. What makes all these threats uniquely dangerous is not just their power, it's their timing. They're arriving together on a planet whose systems are already strained by our daily activities, in a civilization that has become a single, tightly wired organism. In the Permian, if one continent's ecosystems collapsed, others could continue relatively undisturbed. The web of life was local, regional, fragmented. Disasters were brutal, but they were somewhat contained. Today, a drought in one country sends food prices spiking worldwide. A virus that emerges in one city travels by airplane to every continent in weeks. A banking crisis in one financial center can ripple through global trade, idling ships, emptying shelves, and freezing investment in clean technology. We've built a planetary nervous system, a set of cables, satellites, shipping lanes and supply chains that circle the Earth. It allows us to move ideas and resources at speeds evolution never anticipated. It also means that when one node fails, the shock can propagate across the entire network. Ecosystems now mirror this fragility. Industrial fishing fleets can wipe out local fish populations thousands of miles from their home ports. Invasive species hitch rides in ship ballast water and airline cargo holds, jumping oceans in a day. Carbon released in one country warms the air in another, melts ice in a third, raises sea levels against the shores of a fourth. In earlier extinctions, Earth systems fell apart over thousands, sometimes millions of years. We are testing whether they can do it in centuries, or less. Consider what a 6-degree warming world would actually mean. Not a gentle, uniform increase like turning up a thermostat, but a violent rearrangement of climate zones, the tropics expanding, the mid-latitudes baking, the polar regions losing their ice and their albedo, their ability to reflect sunlight back to space. At 1.5 to 2 degrees of warming, we already expect more extreme heat waves, stronger storms, rising seas that nibble at coastlines and displace tens of millions of people. At 3 to 4 degrees, many of the world's great breadbaskets become unreliable. Some regions swing from drought to flood, others simply dry out. Wet bulb temperatures, the combination of heat and humidity, begin to reach levels where unprotected humans cannot survive outdoors for more than a few hours. At 6 degrees, enormous regions of the planet could become effectively uninhabitable for humans and for many of the species we depend on. Coral reefs, which support a quarter of all marine life, would be functionally gone. Permafrost would be melting at scale, releasing vast stores of methane and carbon dioxide, amplifying the warming further. The last time Earth was even close to this hot, there were no ice sheets at the poles. Sea levels were tens of meters higher. Forests grew in what is now the Arctic. The difference then was time. Ecosystems had millions of years to adjust and reorganize. In our scenario, they wouldn't. The oceans would be warmer, more acidic, more stratified. Oxygen-poor dead zones would spread. On land, the pattern of a life-giving rainfall would shift beyond recognition. The insects that pollinate crops, the microbes that build soil, the fungi that knit forests together, many of them would be pushed past their limits. Some researchers have tried to capture this unfolding crisis in a single phrase: biological annihilation. In 2017, two scientists, Gerardo Ceballos and Paul Ehrlich, published a study looking not just at species extinctions, but at what they called population extinctions, local disappearances of once common animals from parts of their former range. They found that even among species that are technically still with us, many have lost most of the places they once lived. A silent thinning, a great retreat. The paper described it as an ongoing, massive anthropogenic erosion of biodiversity and of the ecosystem services essential to civilization. Translated into simpler terms, we're not just losing rare animals, we are hollowing out the common ones as well. The birds that used to fill the sky, the insects that used to splatter against windshields, the fish that used to swarm in coastal waters. It is as if the orchestra of life is still on stage, but most of the instruments have gone quiet. The violins are playing, but the brass is gone. The percussion section is missing. The music is still technically there, but thin, fragile, out of balance. This is what a mass extinction looks like from the inside. Not a sudden cinematic collapse, but a slow, granular emptying. One local population at a time, one forest, one river, one coral reef after another. When the old mass extinction swept through, the survivors were whoever happened to be lucky, or tough, or well-placed. They didn't cause the catastrophe, they just endured it. This time, the catastrophe and the survivor are the same. We are both the asteroid and the shrew hiding in its shadow, and that creates one final unprecedented twist. For the first time in Earth's history, the agents driving a mass extinction can understand what's happening while it happens. We can measure the carbon in the atmosphere, trace the thinning of the ozone layer, map the shrinking ranges of species, run computer models of climate futures. We can look back at the Great Dying, at the Ordovician freeze, at the asteroid winter, and recognize the familiar outlines of our own choices. The next reset, if it comes, won't just be another page in geology's long impersonal story. It will be, at least in part, an authored event. A decision made by a species that knows enough to see the cliff edge forming beneath its feet. The question is not just whether Earth can reset itself again. It can. Given time, it always has. The deeper question is whether our civilization, our cities, our languages, our stories will still be here when the new ecosystems take shape, or whether we will instead join the trilobites, the ammonites, the mosasaurs, and the Neanderthals in the quiet archives of deep time. Because if the next reset comes the way the others did, slowly, blindly, by chance, it will be brutal but familiar. If it comes the way this one is shaping up, driven by a single, aware species pulling multiple levers at once, on a tightly wired, globally linked world, it might be worse than anything Earth has yet seen. And yet, even that is not the end of the story, because after every collapse, something new has always emerged. Imagine you zoom the camera forward, not 10 years, not 100, not even 1,000. Push past all the familiar timelines of politics, technology, and human plans. Keep going until our skyscrapers, our ruins, our languages are fossils, and the last memory of us exists only as a thin layer in the rocks. What does Earth look like after us? To answer that, you have to remember what happened after every reset we've already seen. After the Ordovician extinction, when almost all complex life still lived in the sea, the oceans went quiet. Coral reefs collapsed. Trilobites vanished from entire coastlines. For a while, it must have looked like evolution had run out of ideas, but the silence didn't last. Within a few million years, new lineages of fish, new reef builders, new ecosystems appeared. The world after the dying was not empty. It was different. After the Devonian crisis, when plants had only just begun to claim the land, forests retreated, rivers changed course, shallow seas turned anoxic and deadly. Yet the reset opened space for new groups. Early amphibians, struggling along muddy banks, slowly gave way to the first proto-reptiles. Lungs improved, limbs strengthened. The land that had nearly killed them became their kingdom. After the Great Dying at the end of the Permian, things were worse than anything we can easily imagine. 90% of species gone, whole forests burned or rotted, oceans barely able to support oxygen-breathing life. For millions of years, the Earth was a graveyard remembering what it used to be. And then, atom by atom, it changed. Strange, scrappy survivors, small reptiles, hardy plants, opportunistic invertebrates, multiplied. New coral lineages built new reefs. The ancestors of dinosaurs took their first uncertain steps into vacant ecological roles. After the Triassic-Jurassic event, the last big competitors of early dinosaurs disappeared. What had been a world of many different reptile lineages became, increasingly, a dinosaur world. Long-necked sauropods, swift predators, feathered forms that would eventually become birds. The disaster cleared the stage. Evolution filled it with giants. After the asteroid at the end of the Cretaceous, the skies went dark, the forests burned, the seas acidified. The age of dinosaurs ended in fire and ash. But the age of mammals began in the shadows of that same catastrophe. Tiny nocturnal creatures that had spent millions of years living underfoot suddenly had room to expand. Within a few million years, they became whales and bats, horses and primates. They became us. That's the pattern. Not one reset, 5, maybe 6 if you count what's starting now. Each time, life almost ended. Each time, it rebuilt itself into something completely new. So what does that pattern suggest about a world after humans? First, understand this. If we cause a major extinction, we will not take life with us. We will only take our version of it. The forests you know, the birds you recognize, the specific mix of animals and plants and microscopic life that surrounds you, those are historically recent experiments. They are not guaranteed. They are not permanent. But life itself as a process is extremely hard to kill. If humans vanished tomorrow, Earth would begin reorganizing immediately. At first, it would look like chaos. Cities decaying, roads cracking, dams failing, farmland turning to scrub and then to forest, our domesticated animals struggling, some reverting to wild forms, others vanishing altogether. Invasive species spreading into new territories, using the networks we built, roads, canals, shipping routes, to complete their takeover. Then the slower shifts would begin. Without us constantly burning fossil fuels, atmospheric carbon dioxide would start to drop, but not overnight. It would take tens of thousands of years for natural processes, rock weathering, ocean uptake, burial of organic matter, to pull CO2 back down toward pre-industrial levels. During that time, the climate would stay warmer than anything most modern ecosystems are adapted to. Who thrives in that kind of world? Look at what's already doing well in our disturbed, heated, fragmented habitats. Rats and mice, cockroaches, crows and pigeons, feral dogs, wild boar, certain kinds of ants, certain kinds of weeds, jellyfish blooms in overfished warming seas, bacteria and fungi that can eat plastics, hydrocarbons, even some heavy metals. These are the species that treat human impact not as a disaster, but as an opportunity. In a post-human world, some of them would become the new aristocracy of evolution. Rats, given enough time and isolation, could diversify into dozens, maybe hundreds of forms. Some might become larger, filling the roles of foxes or small dogs. Others might adapt to life in treetops, or along coasts or underground. We know this can happen because rodents have already done it many times in Earth's past. Corvids, crows, ravens, magpies are already remarkably intelligent. They use tools, they recognize faces, they teach each other tricks. A world that has lost large mammals but kept forests and scattered ruins might be perfect for an arms race of bird intelligence. Larger, more social, more curious corvids, generation after generation. Octopuses and their relatives possess complex nervous systems and problem-solving abilities. In warmer, human-altered oceans, cephalopods are already increasing in number. Give them a few tens of millions of years, stable reefs, rich coastal ecosystems, and they might explore entirely new evolutionary pathways, longer lives, social structures, maybe something like culture, but this is speculation, and that's important. Evolution isn't a script, it's an improvisation. What we can say with confidence is simpler. Empty roles do not stay empty. When herbivores disappear, something evolves to eat plants. When large predators vanish, something evolves teeth or beaks or claws to replace them. When forests shift poleward, new species follow the trees. Fast forward not thousands, but millions of years. Our cities are now deeply buried. Their rebar and concrete have crumbled. The tallest buildings have long since fallen, their foundations turned into strange rock layers, rich in metals and glass and ceramics. Asphalt roads have become thin black seams. Landfills have compacted into techno-fossil deposits. compressed plastic, broken electronics, fragmented glass, all welded together. Geologists in that far future, who might not be human at all, would see our presence as a sharp, unmistakable boundary in the rock record. They would find a sudden spike of carbon in ancient sediments, marking a brief, violent pulse of greenhouse gases, a layer rich in microplastics, spread across oceans and continents, embedded in clays and sands, unusual isotopes from nuclear testing, traces of plutonium and other radionuclides, tiny but detectable, like bright radioactive fingerprints, bones of domesticated animals in staggering numbers, cows, pigs, chickens, often in dense, uniform deposits, unlike anything seen in the wild fossil record. Pollen records showing abrupt shifts in vegetation as agriculture cleared forests and planted vast monocultures, then abandoned them. They might call it the Anthropocene boundary, a sixth reset, brief but powerful, compressed into a geological instant. Above that line, they would see something else: recovery. At first, the fossil record would show low diversity, many groups gone, many gaps, strange mixtures of survivors, urban-tolerant species in places their ancestors never lived. Then, slowly, a branching pattern would emerge again. New genera, new families, new forms, warm-adapted reptiles expanding poleward, birds occupying niches that once belonged to bats or small mammals, insects exploring new plant communities, coral reefs rebuilt by entirely different organisms, tolerant of warmer water and more acidic seas. From our perspective, looking forward, this recovery would seem impossibly slow. From geology's perspective, it would be fast. 5 million years, 10 million, 30. These are the timescales on which mass extinctions fade into memory and new radiations take over. Most of the familiar species from our time would be gone. A few generalists might linger, transformed. Everything else would belong to that new world. Would intelligence evolve again? It depends on what you mean by intelligence. Complex problem-solving, tool use, social learning. Those are not uniquely human. They have evolved many times. In primates, in dolphins and whales, in corvids, in octopuses, in some social insects in a very different way. If the conditions that rewarded big brains and flexible behavior persist, then something brainy will almost certainly evolve again. But a technological civilization like ours, with electricity, radio, satellites, global industry, that's harder to say. For 4 billion years, life had intelligence in many forms, but only once did it produce a species that built a planet-spanning technological system and altered the atmosphere in a geological blink. That suggests our kind of intelligence is not inevitable. It is a peculiar solution to a specific set of problems under a specific set of conditions. If those conditions never line up the same way again, there may never be another species that digs up ancient sunlight and burns it, builds data centers, or launches metal into orbit. If they do line up again, perhaps in 100 million years, some descendant of crows or octopuses, or something we can't even picture, might stand in their own equivalent of a lecture hall or a nighttime documentary and tell stories about a strange layer in the rocks. A layer filled with plastic and chicken bones and radioactive dust. A layer laid down by a briefly brilliant, dangerously clever primate that almost burned its world. They might debate what we debated, whether they are alone, whether intelligence is a gift or a trap, whether the future is something you shape or something you survive. In all of this there is a kind of unsettling comfort. Earth will go on, continents will drift, mountains will rise and erode, new oceans will open, old seas will close. Life, in one form or another, will adapt, radiate, invent new ways of being alive. The planet has shrugged off 5 global resets already. It can shrug off a 6th. But that doesn't make our choices meaningless. It makes them more profound. Because while Earth is resilient, this particular version of life is fragile. The specific birds whose songs you know, the forests whose smell you recognize after rain, the coral reefs that exist right now in this exact arrangement of species and colors, the elephants, the whales, the frogs, the pollinating insects, the soil microbes that support our crops, the predators that keep ecosystems in balance. They are the result of hundreds of millions of years of evolution and 5 previous resets. They will not come again in the same way. We stand at a strange intersection in Earth's history. We are both a product of past catastrophes and a potential cause of the next one. We carry in our genes the legacy of ancient survivors and hold in our hands the power to decide how much of the present will join the list of things that only exist as fossils. In the deep future, long after we are gone, the rocks will remember us as a thin line of disturbance, a brief experiment in planetary scale intelligence. Whether that line marks a turning point toward a rich, resilient biosphere or a scar from an avoidable wound is still being written. For now, you're living inside that moment, between the 5th reset and whatever comes next. Listening to the long story of Earth, resting in the quiet between disasters, breathing air made by ancient oceans, standing on ground shaped by extinct forests and vanished seas. You are part of a lineage that survived everything the planet has ever thrown at it. And for a little while, in this narrow window of time, you have the rare chance to decide how gently or how violently you leave your trace in the stone. When you zoom all the way out past the noise of our everyday lives, past cities and borders and years and centuries, you see something unnervingly simple. Earth has reset itself before, not once, not twice, 5 times. Entire ecosystems erased, oceans turned toxic, skies choked, forests burned, dominant species wiped out so completely that if we didn't dig up their bones, we'd never know they were here at all. And yet, through all of it, the planet just kept going. Life fell, then climbed back up again in new shapes, with new plans, new experiments. Fish became amphibians, reptiles became dinosaurs, tiny shrew-like mammals became us. From Earth's perspective, mass extinctions aren't mistakes. They're turning points, sudden edits, in a very long book. We're reading that book now. We just happen to be characters in the latest chapter. When you lie there in the dark, listening to stories about oceans disappearing, forests turning to deserts, skies full of fire, it's easy to feel small, to feel like none of this really involves you. The Ordovician, the Devonian, the Permian, the Triassic, the Cretaceous, they sound like names from a different universe, but they're not. Every breath you take, every bone in your body, every cell that carries the scars and solutions of 4 billion years of evolution, all of it was shaped by those 5 resets. If even one of them had gone differently, you wouldn't be here listening to this. The ammonites that died in ancient seas, the forests that burned at the end of the Permian, the mammals that survived under the feet of dinosaurs, the tiny group of humans who slipped through our own genetic bottleneck, all of them are written into you. Understanding that doesn't just humble you, it arms you. Because now we know something that no trilobite, no dinosaur, no ammonite ever knew. We can see the pattern, we can read the warning signs, rising temperatures, acidifying oceans, collapsing ecosystems, species vanishing faster than they can be named. In the past, life simply endured or vanished. There was no planning, no prevention, just blind survival and blind extinction. But our species is different in one crucial way. We can look back, we can look forward, we can tell these stories, and we can change what happens next. We are the first species in Earth's history that understands what a mass extinction is while it's still unfolding. The first species that can run the numbers, trace the feedback loops, model the climates, and say, if we keep doing this, this is where it leads. That doesn't guarantee we'll act wisely, but it means we can. It means that when we talk about the sixth extinction, we're not just whispering a prophecy, we're holding a choice. We can be just another layer in the rock, a thin smear of plastic and concrete and strange isotopes. Or we can be the species that broke the pattern. The one that saw the cliff edge coming and decided to build a bridge instead of flooring the accelerator. Every time you learn a bit more about deep time, every time you understand another piece of how Earth resets itself, you gain a little more leverage over the future. You start to see how fragile our window is, and how valuable. So as you drift towards sleep, remember this. You carry the genes of survivors who made it through disasters far worse than anything in recorded history. You're living in a moment no other species has ever experienced. You're part of the first generation that can look at Earth's long history of extinctions and say, not this time, not if we can help it. Thank you for coming on this journey through deep time tonight, for walking through vanished oceans and burning forests and quiet, empty worlds, and still choosing to come back to this one, here, now. If these stories helped you relax or gave you something new to think about, it really does help to gently tap the like button. It tells the algorithm that calm, curious content like this is worth sharing. If you'd like more journeys like this across ancient oceans and forgotten continents, you can subscribe and turn on notifications so you'll know when the next story's ready. I'd also love to know where you're listening from. A quiet apartment in a city, a dorm room, a cabin in the woods, a night shift break room. Drop a comment and share your corner of the planet. It's a small way of mapping our own little human meta-population across the world. And if you feel like going one step further, there's an optional YouTube membership for those who want to directly support the channel and help me keep making long, peaceful, deep time episodes like this. It's completely optional. Just being here, listening, is already a form of support. For now, let the ages roll back in your mind, from the first reset to the fifth, from the dinosaurs' last day to our uncertain tomorrow. You are a tiny part of Earth's story, but you're also one of the first characters who gets to help write the next chapter. Sleep well,